Good evening everyone. We are from group 10 and today we are going to discuss about interference testing. Before we begin, let me briefly explain about what is multiple well testing. Multiple well testing requires one producer or injector well and one or more observation wells. Multiple well testing can involve larger radius of investigation than a single well test. Skinning does not affect multiple well tests because the skin only acts in the neighborhood of the active well. In multiple well testing, wellbore storage effects are minimized although not totally eliminated. One of the multiple well testing is known as the interference testing, which is the main topic for today. Before we begin, what is interference testing? Interference testing is a part of multiple well testing and is conducted by producing from or injecting into one of these wells called active wells, and the pressure response is observed in the other well called the observation well. It is a kind of study that is required to understand the effects of pressure communication between the pairs of wells in the reservoir. The active well starts producing at a uniform pressure at time 0 and the other pressure response in one or more observation well at a distance r begins after some time lag. The observation well has a pressure gauge to record pressure and the initial flow rate is 0. It is used to determine whether two or more wells are in pressure communication in the same reservoir, and when communication exists, it can provide estimates of vertical formation permeability K and the average storage capacity, which is the product of porosity times with compressibility in the surrounding of the tested wells. In the homogeneous isotropic system, the porosity, thickness, and the permeability is same everywhere and in all directions. These tests can be used to obtain an adequate reservoir description for homogeneous systems, both isotropic and anisotropic, and heterogeneous systems. Numerical solutions must be used to analyze pressure transient data from heterogeneous systems. At the same time, it is one of the most important and useful tests to understand the well behavior in a water flood and enhanced oil recovery project. In this slide, there is 4 wells. Well 1 is the observation well, and well 2, 3, 4 are called the active well. In well 1, we will carry out the pressure build-up test. The pressure response in well 1 is influenced by changing of production rate of active wells, which are the well 2, well 3 and well 4. The interference testing are used to determine first the reservoir continuity. It is used to determine whether two or more wells are in pressure communication. Secondly is the directional reservoir flow pattern. It is basically used to understand how the reservoir flows. And thirdly is the reservoir permeability K and porosity. When communication exists in two wells, it provides estimates of the average permeability K and the average storage capacity, which is porosity times the compressibility, via calculation and formulas. And last but not least, the fourth factor, which is the nature and magnitude of an anisotropic directional reservoir permeability.
Hi, my name is MAHER KHALED. I will continue for the part which is interface test analysis, simulate analysis method. We have two cases. The first case, which is active well, is producing, injecting. We have here the formula, which is BWS equal to B1 in hour plus M log T, where the BWS is the pressure behavior at the observation. This equation is valid for this equation 0.002637 kT over porosity times viscosity Ct r squared should be less than 100. When plotting BWS with time on simulograph, it yields a straight line portion for slope m, which may be used to calculate permeability and viscosity, where the permeability is equal 162.6 Q viscosity times B over MH, where the porosity is equal to K over viscosity CT R square XP times bi minus b1r over m, all minus 3.2275, where b1 hour is obtaining from the similar straight line at time equal 1 hour. For the second case, which is active well is shot in after producing for time tb, we have the formula pw is equal to b1 plus m log tb over delta t over delta t, where the same thing for the pressure behavior at the observation. This is the formula for case 2. For the equation number 2, when we plotting pw is phase dp plus delta t over delta t on semi-log graph, it tells the same thing as the previous one, as straight line portion for slope m, which may be used to calculate permeability and viscosity. But the difference here is the formula for viscosity, porosity. For the permeability, same equation, 162.6 Q viscosity B over mH. The porosity is equal to K over viscosity St R squared X times to P1 hour minus PWS, where delta T equal to 0 over M, minus log 1 plus 1 over TB, all minus 3.2275, where P1 hour is obtaining from the semi-log straight line at delta T equal to 1 hour. On this case, for the TB plus delta T over T should be equal to TB minus plus 1. This is the graph for the two cases when we plot to get the graph. For the last slide on my part, which is plot delta B base T on log graph and match the field data to the master curve, then pick a match point and calculate permeability and viscosity using the following equation: K equal to 141.2 Kb viscosity over H, all times BD over delta B, for the porosity, which is equal to 0.0002637 K over R squared CT viscosity times T over TD over R squared D. Thank you. This is
Okay, hello guys, my name is Kartigayan. Okay, for my part, I will be explaining about how to solve for interference testing. Okay, there are two methods for interference testing. The first I'm going to explain about the type curve method. Okay, firstly, to generate a type curve, what we're going to need is the change in pressure at an observation valve, which is caused by production or injection at an active valve. Okay, these pressure data will be plotted against the change in time on a log graph paper. Then, this theoretical curve is the exponential integral solution of the line source flow model. Dimensional variables are usually used so that one type curve plot may be used for the analysis of a number of well tests. This graph you see is the type curve that we plotted from the obtained data from the observation well. Okay, on the y-axis you can see it is the dimensionless pressure, and on the x-axis is the dimensionless time over dimensionless radius. Okay, this is the exponential integral solution of the line source flow model. Okay, solving for interference testing, we will be needing a few formulas. Okay, as you can see here, the formula is pressure equals to pressure initial minus 141.2 QB mu over KH. This formula, as you can see, it's derived from the Darcy's equation. Then we'll be using the EI formula as well. Okay, moving on. Okay, we can further simplify this formula by substituting this equations, which are the dimensionless time and the dimensionless pressure formula, and also the dimensionless radius formula. By substituting into the formula, we will obtain the dimensionless pressure, which is negative half EI over times by RD over 40D, and from that equation we can find KH over mu and porosity, compressibility and thickness product formulas. Moving on to the next method, solving for interference testing. This method is called, we're going to use the Cartesian graph. We won't be using any type curve matchings. This is the Cartesian graph. Okay, in this for the second part, for solving for interference testing, we are going to use the Cartesian graph method. Okay, in this Cartesian graph method, we're going to plot a graph of pressure against time. Okay, this method can be used to analyze interference tests in homogeneous isotropic reservoirs. Okay, from after we plotting the Cartesian graph, we will obtain the maximum slope MP and also the time intercept of the straight line whose slope is the maximum slope can be used to calculate approximate values of the mobility thickness product and the porosity compressibility thickness product with the following equation. Basically, from this Cartesian graph, what we're going to do is we just going to plot the Cartesian graph, which is pressure against time. Then we're going to obtain values from the graph, which are the maximum slope MP and also the time intercept of the maximum slope. Okay, after that we can obtain values by just substituting into the formulas of the mobility thickness product and also the porosity compressibility thickness product.
The following is an example about interference testing, where well-test data were obtained from a shallow aquifer. Water viscosity was 0.8 centipoison, formation volume factor was 1 dBl per STB, and system compressibility was estimated to be 12 times 10 to the power negative 5. The formation thickness was approximately 45 feet. Any active well was produced at a rate of 207 reservoir barrels per day, and pressures were observed at a shut-in well 119 feet away. Analyze this data to obtain estimate of reservoir permeability and porous compressibility product. So in addition, we have given here the table. If we analyze this table, we see that from the time where the active well start to produce, there's a change in observation well in terms of pressure from 4.3 hours to 45 hours, where we have here 59.5 psi. So the first thing to do is to identify the most appropriate master type curve, where is exponential integral solution given by dimensionless pressure versus dimensionless time over dimensionless radius square. So the first thing is to prepare our tracing paper, the ruler, our master graph here, the pencil and rubber. The first thing to do is to put our tracing paper on the master type graph, where we draw the dimensions of our master graph here. After that, we see we have here the same dimensions as it is in our master type graph here. So after that, we can plot the points from the data given. We see here the points already plotted. So the next step to do is to move up and down the tracing paper. The lines parallel each other, and we feed the points into the curve here. So let's see how it looks like. So we have here our points matched. Our points matched in the curve. So we choose the points which is match point, where the time is 100 and dimensionless pressure is 10. Delta P is 10 and dimensionless pressure is 0.3. Here it's approximately 1.05 TD over RD squared. So after that, we have here our pressure match, delta P 10 psi dimension express 0.3, we can calculate from this data, we can calculate permeability using this formula here. By substituting the data into this form, we can have this equation here where we have only one parameter, permeability, and we solve this equation for permeability, we get 20.3 millidars. So the next step is to use time match. From time match, we can calculate the product porosity compressibility using this equation here. So the R here is the distance between the wells, and the rest, all the parameters are given. The permeability we calculated previously. Solving this equation for product porosity compressibility, it leads us to 4.5 times 10 to the power negative 5. And compressibility, we are given the problem, which is 12 times 10 to the power negative 5. So solving this equation for porosity, we have 0.375. Well, in a conclusion, from the given data, it's clear that the both wells are in communication, since there's a change in terms of pressure when the times varies from 4.3 to 45 after active wells start to produce. In addition, translating this data into the graph, we were able to calculate the permeability, which the average permeability was estimated to be 20.3, and the product compressibility asked in the problem was 4.5 times 10 to the power negative 5. So solving for porosity, we have 0.375.